This is an interesting question. Gave me kind of a hard time. Power xn. So we want to take the double value to the power of n, which could be any number between minus 2 to the power of 31 all the way up to 2 to the power of 31 minus 1. And this is just the range of an integer. Okay, so that's pretty easy, right? To take the power of something, you just multiply it by itself n times. So 2, say x is equal to 2 and n is equal to 10, then we'll do 2 times 2 times 2, and keep doing this until we have 10 of these 2's, and that will be equal to the power of 10, right? But yeah, there's a problem. If we have a 2 to the power of 31 minus 1, which is possible, and it could be up to this huge number here, that would also give you a really huge number, which wouldn't fit in a double, I don't think. So they do give some constraints. So they say that the x power of n is in between minus 10 to the power of 4 and 10 to the power of 4. So that means this has to be, so whatever the power is, this is always less than or equal to 10 to the power of 4. And yeah, and we realize that this is actually like around 13.5-ish. So if you do 2 to the power of 13.5, you get 10,100, 11,000 something. So maybe 13.2 or 13.3. Yeah, around 13.3, which is a bit over 1,000, but let's say that. And so, okay, so that's just let's just say 13 2's, because n is an integer, it can't have a decimal value, then we'll just multiply 13 times. That should be calculated pretty quickly, but there is a problem. What if our number, so if our x value is less than 1, so if our x value is in between 0 and 1, if x is 1, then 2 to the power of 31 is valid, because the answer will always be this. This will always equal to 1. Okay, maybe we could just handle that in the base case, and we don't have to go through in the loop, which iterates through, has 230 to the power of 31 minus 1 loops. We could handle this in an if condition, but what aren't there other cases? Like you have 0.9 to the power of 31 minus 1. If you take the power of a positive power of a number that's in between 0 and 1, you'll get a number going towards 0. So that's also a problem, because our loop would go through this many iterations until we get to the answer. So how do we speed up this process? I mean, so I'm saying it's too slow, but how do we know it's too slow? How can we know that 2 to the power of 31 can't work? So we can, as a rule of thumb, if we can do around 10 to the power of 8 operations per second, and we can assume that if they don't really give a time limit, I just kind of assume that the time limit is 1 second. So 2 to the power of 31 is definitely greater than 10 to the power of 8. It's 2 to the power of 31 divided by 10 to the power of 8 is 21 times larger, so it will take around 21 seconds if I want to have a loop with this many iterations. Just as a ballpark estimation. So to solve this problem, you have to think about the binary representation of this power. So n here, if n is equal to 10, for example, in binary, that's represented as, because a 10 is equal to an 8 plus a 2, in binary that means, so I have a 0 for the 2 to the power of zeros, a 1 for the 2 to the power of 2s, a 0 for the 2 to the power of, and a 1 for the 2 to the power of 1. To the power of 2s, because that's 4, and 1 for this. So this is the binary representation for 10. Why though? So this is 2 to the power of 3. This is 2 to the power of 2, 2 to the power of 1, and this is 2 to the power of 0. Like that. And if this is the binary representation, we can find the decimal value of this binary representation by just adding up the powers of 2 that correspond to a 1 in the binary representation, in the binary string. Now this is very similar to the idea that we're gonna use this idea to help us solve this problem efficiently. So that idea is, if we want 2 to the power of, so let's say x to the power of n, let's say x to the power of, say 10, x to the power of 10 will be equal to x to the power of 8 times x to the power of 2. So it's like the same idea. So if you can figure out what these are efficiently, we can figure out what this is, and just accumulate the answer as we go along. So we can go through and figure out what x to the power of 1 is, which is just x. Then we can figure out what x to the power of 2 is, which is just the previous value multiplied by itself. So we get this. And if we keep going, we get x to the power of 4, which is x to the power of 2 multiplied by itself, so on and so forth. X to the power of 8. And the maximum we'll get up to is actually 2 to the power, x to the power of 32, I think. Is it 32? I think it's 32. Oh, we'll see. Can't really think about that at the moment. And then let's think of the binary representation for 10 again. So 10, if we just reverse this the other way, we have 0, or 1, a 0, and a 1 here. And that's what we get. So we have x to the power of 2 plus and x to the power of 8. So multiplying these two together will give us x to the power of 10. So hopefully that makes sense. Let's try a different one. So if you have x to the power of 15, 15 in binary is what? It's so what's the efficient way to convert a decimal value to binary? Is you think about what's the highest power of 2 I can fit in 15? 8. So that's 8. What's the next highest power of 2 that can fit in the gap between 15 and 8? So if you do 15 minus 8, 7. So what can fit in 7? Highest power of 2, probably a 4. So x to the power of 4. And then we have a 7 minus 4, you have a 3. Highest power of 2 that can fit in a 3 is a 2. And then we have 1 remainder, and then so that is just going to be x to the power of 1. This is multiplication. Oops. So if I multiply all these together, I'll get this. And these I'll figure out by just starting from this, multiplying by itself to get this, multiplying by itself to get this, and then I just check the binary digit and see if it's a 1 or not. If it's a 1, then I multiply the corresponding power of x with the answer. And the answer would start with a 1. Yeah. So how would I so first I know I need to build up this in each iteration of the loop. I would have to, the first iteration I would have this, second iteration I would have this, third iteration I would have this. So one thing we have to handle though is that if n is negative, that's also a problem. If n is negative, we can first do it just like it's positive. So say for example here, if you do it like it's positive, so that will just be 2 to the power of 2, which is 4. And then we just do, the answer will just be 1. If n is negative, then we just do 1 over that answer. Because that's easy, so we just do it in positive first and then figure out if it's what to do if it's negative. But first we have to go through all of these. So we can start with maybe say power x. Power x is equal to x initially, and we'll have a for loop that goes through all the bits in n. So we have int I is equal to, so we take the absolute value of n and we step through the bits of I. So I would go, well I does not equal to 0. Oh, that's a problem. That might not work. Let's do it a different way. Yep. Let's do, for int I is equal to 1, I less than equal to 32. Right, so there's 32 bits in an int, so we just have to go through all of those. And at each iteration, we keep track of an answer, which starts at 1. And we also do, yes, so we check the first bit in the string. So this is, say this is 10, the binary representation of 10. To check if this is a 1 or not, we do a bitwise AND with that value. So we can do, keep track of, say say p is equal to n initially, so absolute value of n. Then we have if p and 1, so that's checking the rightmost bit of p, seeing if it's turned on. So if it is turned on, then I want to do answer times equal to power x. Then to get to the next iteration, I want to just do power of x times equals to power of x. So I'm multiplying it by itself. And at the end, I need to do, if n is less than 0, then answer is equal to 1 over the answer, and then return the answer. So let's kind of step through this, see how it works for this here. So if n is equal to 10, we have a bounding string that looks like this, 1 0 1 0, and at the front we have like 28 more zeros, but we'll just ignore those for now. Eventually we'll actually be going through all of those, but we know they're all zeros. But we won't be doing anything with those because we know that they're all zeros, and we only add to the answer if there are ones. So first we see initially that our power x is equal to 2, because we're doing this example here. So, and the answer is equal to 1, so we're currently at this position. At this position, we query using this bitwise statement if this is a 0 or 1. If it's a 1, then this is a non-zero value. So this will return true, and I will add 2, I will multiply 2 to the answer, but since it's 0, I don't do anything. And then we move that across. Oh, we don't actually move it across. Oh, I just forgot a step here. We do p bit shift to the right once. So if you bit shift to the right once, that means all the bits move to the right one place, because we have a bit shift by 1. So that really is doing this. We get rid of the 0, that 0 falls off the end, and we add another 0 at the front here. And then we query again in the next loop. But we'll also do this. We multiply power of x by itself to get 4 now this time. And we see that this is 1. Okay, so it's 1, so I multiply answer by 4. And the same thing, I bit shift to the right, so the 1 falls off the end, and I insert a 0 at the other side. Query again does nothing, but 4 also multiplies by itself to get 16. And then this one and yep, so here we don't do anything. Wait, hold on, I'm confused. That was a 4. Okay, and then we do that. So 16. But we don't do anything with 16 because this is a 0. And then we bit shift again. And we see that's a 1. When we bit shift again, we'll also make sure we update this so it's 16 squared, or 16 times 16, which is 16 squared. So 256. And then we see it's a 1, so we multiply 256 with 4, which is 1,224. Wait. No, 1024. Oops, my math. And that is correct, yes, 1024. Okay, so hopefully that makes sense and works. Okay, yes, that works. So initially I was going to show the other way of doing it. See, the other way of doing it is I could start I at abs of n, and then change the for loop so that I have I not equal to 0, and then do plus plus I, replace that with a bit shift of 1. Right, so that's essentially doing what this is doing. And I'll have I. Alright, so this will work for most cases, but there is a case where this fails, and it's a bit too difficult to understand. If the 32th bit is a 1, and a bit shift to the right, what happens is I drop off one off the right end, and then I insert either a 0, I insert a new bit to the left hand side, but that new bit could be a 0 or a 1, and that depends what the leftmost bit is. So if the leftmost bit is a 1, then I insert a 1. If the leftmost bit is a 0, then I insert a 0. Since it's a 1, then I insert a 1, and as I keep doing this, I never becomes 0. So I don't know where to stop. So this will just loop on infinitely. So I need to make sure I either use an unsigned int. So if I use an unsigned int, because this is the reason why we have this behavior is because this is a signed int, but shifting the right, for reasons to keep the sign valid. Signed value valid, then I have to insert 1s. But if it's unsigned valid, then it doesn't matter. Just insert 0s. No matter what the leftmost bit is, just keep inserting 0s if you bit shift to the right. So I can make I an unsigned int, and this should work. Yeah, that also works.